Hey, workshop students. I thought I'd make another video with a question. This happens to be your question that has a block on a ramp. But I thought also before I went too far on this, that I would share with you a little technique that I like to use when I'm solving anything involving what we call dynamics, Newton's second law or first, second, and third law of motion. And also, there's two other little hints I'll give along as I'm solving this problem. But I wanted to give you the big picture and I encourage you maybe to remember these four steps because these problems can get pretty tricky. But they really boil down to four steps that make it sound kind of simple. But if you could follow these four steps, each one makes the next one easier, and hopefully then the problem will be easy for you. So I like to say this. And in step number one, make sure you get a good physical picture of what's going on. Whether that means actually drawing something or just have it in your head doesn't really matter. But as you will soon discover, the wrong physical picture makes you do things that are just, nonsensical to the problem. It doesn't make any sense, or you don't see things that are actually given because you don't have the right mental picture of what's going on. But a good physical picture then leads to a good free body diagram, or I should say diagrams, which I'll label as F, B, D. Because your harder problems will have more than one diagram, but the easy ones will just have one diagram. And so I did one already with the static object with ropes with a free body diagram, and this one here that I'm about to do, you'll see that. But a good physical picture leads to a pretty simple free body diagram. And the free body diagram, if done well, should lead to a step where I'll say you now then write out the equations. And so you take Newton's, in plural, equations. You take Newton's first, second, and third law, mostly the second law, and you write out those equations. And you write them out by looking at the free body diagram. And of course, you get the free body diagram by looking at the physical picture. So if a good physical picture led to a good free body diagram, then that free body diagram should make an easy step to write out the equations. And then you solve those equations. And those are the four big steps. And anything involving forces and accelerations really involve these four steps. So for the next 2 weeks, and maybe even more, but these two chapters here, chapters 5 and chapter 6, all really boil down to this. Now, some problems are harder because maybe the math is hard. Maybe there's two equations, two unknowns, although that's not too bad. The harder ones are four equations and four unknowns. Those can be the hard ones, where they have two or more free body diagrams. And so those are the tough ones. Anyways, let me encourage you, this is my advice, is to remember these four steps. Good physical picture, free body diagram, write out the equations, solve the equations. Okay? All right, and hopefully I can illustrate that with this problem here. All right, so let's read this problem here. So this problem simply says that a block with a mass of 3 kilograms slides down a ramp that is inclined at 40 degrees above the horizontal. All right, so maybe I'll just kind of make an incline that is at 40 degrees. And it says we have a block, and so maybe I'll just make kind of a rectangular looking block. I'll put 3 kilograms over it. Okay, so I got this 3 kilogram block. It's sliding down the ramp. Okay, so here it is moving its way down the ramp at 40 degrees above the horizontal. Now, the block starts from rest, okay, so really they said, you start with an initial speed of 0 here, and it slides down a distance of, and so it's going to go some distance down 2.06 meters, down a frictionless, okay, so this is actually one of the easier problems, no friction involved, and it makes sense, you're just now building up to more complicated forces, but so frictionless surface. At the bottom of the ramp, the block speed is v, solve for v. All right, so we're trying to find the speed down here at the bottom. Okay. And what maybe makes this problem kind of hard is it's actually kind of a combination of the previous stuff we did and this stuff. You see, if I think about the kinematics problems, if this is a constant acceleration problem, I got to prove that to myself. But my thoughts are, okay, I could get final speed by saying it is a initial speed plus acceleration times time. And I'm looking for this, the final speed. I'm given the initial one. I'm not given the acceleration. I'm not given the time. Now, the other equation is final position is equal to initial position plus initial velocity times time plus 1/2 acceleration times square. All right, so if I think of the x-axis as kind of going down the hill here, I do know the initial position, if I call that 0 and it goes down, so I know final position, okay, and I know initial speed, and that means then if I can get the acceleration, from here I can get time, I can put into here and then get final speed. So really the thing is saying here that I can use these kinematics equations. I guess I still have to prove to myself that it's a constant acceleration, but if I can get that constant acceleration, if I can figure out what that acceleration is, I can put the acceleration then into here to get time, and then take the time, put it into here with the acceleration and get the final speed. So that's kind of what I'm thinking. That's kind of my game plan. But all of that is conditional upon finding the acceleration. And of course, it makes sense then why it's in this chapter, because this chapter is all about, writing out the equations, these equations being Newton's 3 laws. And particularly the second one has acceleration in it. So that's what I'm going to do. I'm going to do a free body diagram involving the forces. The forces are going to lead to the acceleration. A nice little picture I like to say is add up all the forces. That leads to net force, which is ma, and so then we can get A. Now, once we get A, we can go through this idea of A leads to V, and V leads to T, or in this case, I'm going to actually go the other way around. I'm going to use the X to lead me to the V once I get the T, okay? So that's, again, kind of my thinking in this. So let me get to the heart of the problem finally. Hopefully I haven't talked too long. Oh wow, I'm 8 minutes in and I'm just now really getting to the heart of the problem. But I want you to see that here. And I would even say that I've probably back here a few moments ago when I was drawing this picture really got step 1 accomplished. A good physical picture of what's going on. I got a block on a hill and it slides on down. Okay, there is no friction involved. I know a few parameters like the angle of the hill, the mass of the block, the distance it slides. I know I'm looking for the final speed, and I know the initial speed. So that's this first one. That's what I would call the good physical picture of what's going on. Because that should lead me to step 2, which is the free body diagram. All right, so the free body diagram really means this, and this is where the name comes from, free body. What it means is take the object that you're focusing on, which in this case is the block. Draw it and no other objects, okay? No other objects are supposed to be drawn here. That's why it's called free body. The only thing you add into this diagram is forces, because the motion of this block is determined by the forces on it. It doesn't matter where they come from, what kind. They could be magnetic forces, they could be electrical forces, they could be gravitational forces, they could be the tension from a string, they could be frictional forces. They could be normal forces. They could be a force from a spring. I mean, there's a lot of different forces that we will talk about. But the real bottom line is where they come from isn't as important as just there is a force. Because Newton's second law says you add up all the forces, that leads to the acceleration. So we don't need to really specify, once we get to this step, where those forces are coming from. All we need to do is to label where they are, or I should say what direction they are and how big are they. And I like to say this, that the obvious force is the force of gravity. Gravity pulls down and is equal to mg. And then everything that touches it. Now, the incline would go here. I don't want to draw the incline, but the incline would push sideways to the incline or perpendicular to the surface. And so we call that the normal force. And some books use the symbol little n, but I think your OpenStax book use F sub n, if I'm not mistaken. Oh, bummer, and I don't have quick, easy access to your survey book, or do I? Let's see. I got volume 2 up here because I was working with some 121 students. Let's see if this is worth our efforts. Outline, free body diagrams, forces, force 1, force 2. Yeah, I'm probably just wasting your time here. I'll figure out the notation later, I guess. Yeah, I don't see anything real quick. I still haven't got anything they call a normal force. Second law. Ah, there it is. Normal force. Ah, and they use a capital N. All right, good. So hopefully that was worth the effort. All right, so I've got a normal force pushing perpendicular to the surface. And that's it. Now, if it was a friction surface, then I would have an additional force from the contact. But at this point, I just have these two forces. And this is what I was trying to say, and I'm really trying to illustrate, even though it's going to make the video kind of long, is I'm trying to illustrate these 4 steps, all right? And this good physical picture hopefully led to this, the free body diagram. And again, that free body diagram is drawing just the forces. So we just know the force, one force is mg and the other one is n. That's all that matters, and that's what I'm trying to illustrate here. We don't really care anything more about those forces. That's why we don't draw the other object. That alone determines the motion of the block, because I'll say it again, the block is determined by all the forces on it. So that's why we want to label just the forces on the block. It helps organize our thoughts. So this is a good and important step, okay? Well, now I'd say now I'm done with step 2. I've drawn a free body diagram. All right, well, on to step 3. In step 3, I would say, write out the equations. And there's a motion in the x direction, or forces in the x direction, and motion and forces slash in the y direction. So I'm going to split my paper, like I've been trying to illustrate in a couple other videos, so I can do my equations for the x and my equations for the y. And what I mean here in step 3 is write out the equation. So what we know is we know that the sum of all the forces in the x direction equal mass times the acceleration in the x direction. And we also know that the sum of all the forces in the y direction equal mass times acceleration in the y direction. So that is Newton's second law, applied twice, one for the x and one for the y. All right, now, before I can go any further with writing out the equations, I need to really come back to my free body diagram and say, well, what is the x direction and what is the y direction? And of course, you can imagine it doesn't matter what you pick as your grid. But I will give you what I consider a helpful hint. If you know the acceleration of the block, which you would have to get that back from the step one, the physical picture. But if you know that, I would say draw one of your axes, and usually I just pick the x-axis, but it really doesn't matter. But draw one of your axes in the direction of the acceleration, okay? That tends to make the equations the easiest. Now, it's not the only way of doing it. So you could draw your axes any way you want. And some people would be tempted to draw the traditional axis and maybe call, this the x-axis and this the y-axis. And would it work? Yes, it would. But I will tell you that it will be much easier if we draw an axis so that, let's say, the x direction is the direction it accelerates. So what I'm going to do is I'm going to come back to my physical picture and say, well, what it does is it kind of slides down the incline. So I'm going to take a non-traditional axis, so in green here, and I'm going to call that the x-axis. Now, of course, perpendicular to that must be the y-axis. So once I've established what the x-axis is, I can then also establish what the y-axis is. So I'm going to use this axis. I'll say it again. There's nothing wrong with using the traditional one. In fact, there's nothing wrong with doing any axis. Any axis you can think of. Put the origin anywhere you want. Put the axis anywhere you want. It will work. Where you choose to do your math doesn't change the physics of it. So it would work. But I'll say it again. I am going to deliberately, if I know, or if I don't know, make my best guess, and set my x-axis to be the direction of the acceleration. And this problem is straightforward enough that clearly it slides down the incline. That is the direction it accelerates. Okay. Now, you may say, well, now wait a minute. That doesn't look so good because now the force of gravity is not along the y-axis anymore. And it is not along the x-axis. You're absolutely right. It's not. So that made, I would say, this maybe a little worse. However, you will notice that by tilting it, now the normal force is along the y-axis. So I gained there. But I'll say it again, both of those are not that big of a deal compared to what I really gained. What I really gained then is the acceleration right here. The acceleration on the x-axis is the whole acceleration. And there is no acceleration on the y-axis. That's really the best advantage you can have. You don't have to put like cosine of something here or sine of something here. Then you don't have to get the x and y components, and then you don't have to square them and hook them up together. What you can do then is just solve for the acceleration right here. The acceleration in the x direction is the whole complete acceleration, and more than that, this side is 0. So there's no sine or cosine over here. There's a 0 over here. There's no ax squared plus ay squared, getting the square root using Pythagorean's theorem. There's none of that. So that is really the big advantage. So I'll say it again, and hopefully I'm not being too long-winded here, but your best advantage here in step 3, when you write out the equations, is to write them out on a grid that is not a traditional grid, and maybe that'll be the hard part for you, because if it's non-traditional, you're not used to working with a tilted grid. But trust me, you will learn to appreciate it and the simplification it does to the mathematics. All right. So now that I have a chosen grid in green, I can actually follow what I was saying. All right. So let me add up the forces in the x direction. Now, this is where a good free body diagram makes step 3 pretty easy. Now, I've kind of covered one of my forces here, the normal force, with my axis. And so remember, there's the normal force and then there's the gravity. If I look at the normal force, it's all in the y direction. So over here, I would say 0 amount of force in the x direction from the normal force. Now, if I look here, this then would be, and if I break it into its components, maybe I'll try to find a different color. Do I have a different color that'll stand out? Maybe this purple will stand out. But this is kind of the hard part of tilting my axis, is I have to realize now that the force of gravity has this purple component, which would be in the negative y direction, and then this purple component, which would have the plus x direction. So this would be plus mg, and sine or cosine, depending on what angle you look at, maybe I'll look at this angle here. Let me call it theta. And so this would be opposites of theta. So that is how much of the force of gravity is in the x direction. That little purple piece right there would be mg, and it would be opposite of the sine theta. And by the way, this purple piece, which I'm going to need in a moment, would be mg, and it would be adjacent. So it would be cosine theta. Okay? And that'd be the y component. But that's what I need over here. So I'm getting ahead of myself here. So, all right. So I think I've done it. I've got two forces, and I've now added up the x component of each of them. For the normal force, I got 0. And for the gravitational force, I got a plus mg sine theta. And that has to equal to ma. And notice I'm just going to put an a here. That's, again, the advantage. This is not the x component. This is the full acceleration. Okay. And so I would say that is half of step 3. I've written out the equation. Okay, let me do the same thing here. Let me write out the equation. All right, so let's come back to the free body diagram. Let's look at the forces involved. All right, there's, again, 2 of them. There's the normal force. Okay, so here's the normal force. And when I say the y direction, I would say all of it. So that would just be n. And it's all in the plus direction. Now, how much of the gravitational force is in the y direction? And that would be that little purple piece. As we said, it would be an mg, and it would be adjacent to the angle theta. And it, of course, would be negative direction. And that would have to equal, and again, this is the advantage of getting that grid, 0. There's no acceleration in the y direction. We picked our x direction so that the block moved in that x direction. So it didn't move anything in the y direction. So 0 acceleration. Okay, so there's step 3. So then step 4 is solve this. Now, if I solve the y direction, I get normal force is equal to mg cosine theta. Now, this problem did not ask for the normal force. So in one sense, that was unnecessary. But I do know this, that you are going to be asked to do this in the future. So this is kind of the easing you into it. But you're going to see that if this one involved friction, in order to answer how much friction there have, you first have to do the normal force. So that could be useful if there was friction. For this problem, it's not really useful. But nonetheless, I'm going to calculate it. The mass, as we said earlier, was 3 kilograms. G, we know, is 9.8. And this would give me a chance to ask the question about, well, what is theta? Now, probably the best way to kind of think about it is, remember that theta is now this angle from what would have been straight down. So here's gravity straight down, but then we we twisted our axis. So if we had made the traditional axis, this would have been straight down, and then we twisted it. Well, take that mental picture back up to here, because if you go straight down and then you twist it so that it's here, how much do you twist it? Well, I would say it's the same thing that you did over here. Remember, the x-axis would have been horizontal, and you twisted it until it got down to the same as the incline, which means you're twisting it 40 degrees. These are alternate interior angles. So the twist of the x-axis is to twist it 40 degrees, which would mean the y-axis also must twist 40 degrees. So this twist angle, if you will, of my grid is also the slope of the incline, the 40 degrees. All right. So again, I know the problem didn't ask for this, and I'm probably making it harder and longer than needs be, but I wanted you to just to kind of have the big lesson here. Let me check if I'm in degrees. I am. So this would be 3 times 9.8 times the cosine of 40 degrees. And this would say the normal force is 22.5 newtons. And again, like I said, not really necessary for this problem because it didn't ask for the normal force. And like I said, most of the time you need to solve for normal force before you can get friction. And so when you start doing friction problems real soon, you're going to need to do that step. So we could actually make this, a simpler step. I never even have calculated this, but let's do this one. So this would be the mass. Actually, you can see the mass shows up on both sides, so I'll just cancel it off. And so this will be 9.8, and then this would be the sine of. And we just argued that the angle would be 40 degrees, and so the twist angle is 40 degrees. And so that's how we're going to get the acceleration. So the acceleration down the incline is 9.8 times the sine of 40 degrees, which makes an acceleration of 6.30 meters per second squared. And that's the real part of this problem, is getting the acceleration. Because once I have the acceleration, I'm going to go back to what I said, which would be from the previous chapters. So let me do this equation. So final position is equal to initial position plus initial velocity times time plus 1/2 acceleration times squared. So starting at position 0 and sliding down until you get to a position of 2.06, starting with an initial speed of 0 and now having an acceleration of 6.3, I can now solve for how much time does it take to go down the incline. So 2.06 multiplied by 2 divided by the last answer, and then taking the square root gives me a time of 0.809 seconds. And then as we mentioned earlier, once I have that, I can put it into this equation, the first equation. Oh, by the way, just reminded myself that, hey, notice I got the acceleration. Notice it's just a number. It doesn't change with time. It's a constant number. So this is my proof that the acceleration is constant, which is justifying using these equations. Because remember, these equations are only valid for constant acceleration. But that's what I've proven here. Not just the number, but proven that it's a number that doesn't change. So it's a constant. All right, so initial speed would be 0. Acceleration, as we just said, is the 6.3 meters per second squared. And the time is the 809 seconds. So this would be the 6.3 for the acceleration times the last answer. And it looks like we're looking at about a 5.09 meters per second for the final speed. Or the two significant figures, 5.1 meters per second. Let's see, how many significant figures do we want? Oh, yeah, it said 3.0 kilograms. So back here, I should have put 3.0. So there's 3 significant figures and there's 2. So my final answer should just have 2 significant figures. So 5.1 would be the better answer here. Now, by the way, one more thing, even though this has gone on for a long time, just to remind you that these 2 equations could have been put together and gotten v squared final is equal to v initial squared plus 2 times acceleration times the distance traveled. I put them together separately, but using this would have made this just one step. So it would have been kind of nice just to put a 0 squared plus a 2, the acceleration 6.3, the distance 2.06, and if you go to solve for final speed, you would then get 2 times 6.3 times 2.06, and taking the square root of that, we've got the same answer. And so 5.1 meters per second when you're looking at 2 significant figures. So using the old stuff, hopefully you're getting really good at, but what's new really are these 4 steps. And that's really what I wanted to spend a little extra time. Commit those to memory. Good physical picture leads to a good free body diagram, which leads to an easy way to write out the equations, which then leads to a bunch of math to solve it. All right. Hope that helps.